Beneath the serene meadows and geysers of Yellowstone National Park lies one of Earth's most powerful geological forces, the Yellowstone Caldera, a supervolcano stretching across Wyoming, Idaho, and Montana. This volcanic field, driven by the Yellowstone hotspot, is a complex of 4 overlapping calderas, formed by cataclysmic eruptions over millions of years. It began 2.15 million years ago, with volcanic activity continuing through 3 major cycles, each culminating in a super-eruption. The first of these, the Huckleberry Ridge Tuff eruption 2.8 million years ago, was the largest, forming the island park caldera. It unleashed over 2,450 cubic kilometers of magma in a series of explosive phases, followed by caldera collapse. This event blanketed North America in ash, with fallout detected as far as the Pacific Ocean and Texas. The force was so immense, it reshaped the continent's atmosphere and climate. The Yellowstone hotspot is not a product of local tectonics, but part of a 16 million-year trail of rhyolitic volcanic centers stretching across the Snake River Plain. This linear progression, from older calderas in Idaho to Yellowstone, suggests a deep mantle source. Scientists debate its origin. Some propose upper mantle dynamics from the subducting Farallon plate, while others point to a mantle plume rising from near the core mantle boundary. Seismic tomography has revealed a cylindrical thermal anomaly beneath Yellowstone, supporting the mantleplume theory. This plume, now feeding the hotspot, previously erupted the Columbia River basalt group. As the North American plate drifts southwest, it moves over the stationary plume, creating the age-progressive chain of volcanic fields from McDermott to Yellowstone. Before Yellowstone, the region experienced intense andesitic volcanism 53 to 43 million years ago, forming the Absaroka volcanic supergroup. Eroded peaks like Mount Washburn and Eagle Peak are remnants of these ancient stratovolcanoes. But Yellowstone's volcanism is unrelated to this earlier activity. It is part of a new, hotspot-driven system that reshaped the continent's volcanic landscape. The Yellowstone Plateau disrupts the Laramide orogenic belt, a mountain-building zone formed in the late Cretaceous. Unlike those tectonic forces, Yellowstone's volcanism is driven from below by a deep-seated heat source that melts rock, generates magma, and fuels one of the most explosive volcanic systems on Earth. From 2004 to 2009 GPS and satellite data detected rapid uplift in the Yellowstone region, attributed to magma intrusion beneath the surface. Though alarming, scientists at the Yellowstone Volcano Observatory emphasize that this does not signal an imminent eruption. The magma reservoir contains partial melt, but it is not currently eruptible. Most of it is too solid and too deep. The 2005 BBC Discovery Channel film, Supervolcano, dramatized a potential future eruption, sparking public fear. But scientists stress that while Yellowstone will erupt again, it is not overdue. The cycles are irregular, and the next event could be thousands or tens of thousands of years away. Yellowstone's volcanic field contains 4 calderas, each formed by collapse after massive eruptions. The first, the Island Park caldera, was created by the Huckleberry Ridge Tuff. Its northern and eastern boundaries are buried, but Big Bend Ridge in the southwest is interpreted as part of its ring fault. A fault along the Snake River may also mark its northern boundary. The second cycle caldera, the Henry's Fork caldera, formed 1.3 million years ago during the Mesa Falls Tuff eruption. Thermon Ridge in the northwest is inferred to be its caldera wall. The same Big Bend Ridge fault was reactivated, collapsing again. Though basalt flows cover its southern edge, gravity data reveal a circular structure about 19 kilometers wide. The present Yellowstone caldera, formed 640,000 years ago, is a compound structure with 2 overlapping ring fault zones centered on the Mallard Lake and Sour Creek domes. These resurgent domes rose after collapse due to magma pressure below. Lake Butte and Lewis Falls mark parts of its rim, though the full boundary remains uncertain. Recent field studies challenge earlier models. The eastern caldera boundary may lie west of the Sour Creek Dome, following the Yellowstone River. The southwest edge is obscured by younger rhyolite flows, making precise mapping difficult. This complexity shows that calderas are not simple circles but dynamic, evolving structures. West Thumb Basin, the western arm of Yellowstone Lake, is an elliptical depression 6 kilometers by 8 kilometers. It is interpreted as a 4th caldera formed by a smaller explosive eruption during the 3rd volcanic cycle. It hosts one of the lake's deepest points and remains thermally active, with hydrothermal vents and hot springs along its floor. The volcanic plateau includes lava domes, crater lakes, and bimodal lavas, both basaltic and rhyolitic. Basalt flows typically erupt along caldera margins, while rhyolite forms domes and explosive tuffs. Together, they cover about 17,000 square kilometers, though erosion and burial have altered their original extent. The plateau structure reflects repeated cycles of magma buildup, eruption, collapse, and resurgence. Each caldera formed over a shallow magma chamber that emptied catastrophically, causing the ground above to sink. Then, new magma intruded, uplifting the floor and forming resurgent domes, a cycle of destruction and renewal. The first volcanic cycle, from 2.15 to 1.95 million years ago, began with the rhyolite of Snake River Butte, erupted 2.14 million years ago near Ashton. Its vent lay close to the future caldera margin. This was followed by the Junction Butte basalt, a 60 to 70 meter thick flow on the plateau's northeast edge, dated to 2.16 million years. The cycle culminated in the Huckleberry Ridge Tuff eruption, 2.077 million years ago. It began with a Plinian phase, ejecting ash up to 2.5 meters thick at Mount Everts. Multiple vents sourced this initial phase, which lasted weeks and evacuated about 50 cubic kilometers of magma, triggering caldera collapse. The eruption then shifted to pyroclastic flows, the ash flow tuff phase. This consisted of three members, A, B, and C. Member B, the largest, erupted from north of Big Bend Ridge after hiatus. Member C, smaller and later, tapped rejuvenated magma near the Red Mountains, where the tuff reaches 430 meters thick. The Huckleberry Ridge Tuff had a total volume of about 2,450 cubic kilometers. Glenn Azette estimated another 2,000 cubic kilometers of ash fell across North America, forming the Huckleberry Ridge ash bed. This tephra layer has been found in deep sea cores 1,600 kilometers from Yellowstone, as well as in California, Iowa, Arizona, and Texas. After collapse, rhyolitic lava flows erupted within the caldera. The Sheridan Reservoir rhyolite, dated to 2.07 million years, flowed at least 20 kilometers from the ring fracture. Two other flows, Blue Creek and Headquarters, erupted later at 1.98 and 1.95 million years with a combined volume of 10 to 20 cubic kilometers. After 500,000 years of quiescence, new magmatism began north of Big Bend Ridge. The Bishop Mountain Flow, a 375-meter-thick rhyolite, erupted 1.458 million years ago. The Tuff of Lyle Spring followed, a 1 cubic kilometer ash flow sheet with 2 cooling units. But these may not belong to the second cycle. Tiffany A. Rivera and colleagues argue in 2017 that these eruptions came from a separate, localized magma chamber, the Lyle Spring magmatic system, distinct from the main second cycle source. This highlights the complexity of Yellowstone's volcanic history. Not all eruptions fit neatly into cycles. The true second cycle caldera-forming event was the Mesa Falls Tuff eruption, 1.300 million years ago. Preceded by the Green Canyon flow, which was truncated by the Henry's Fork caldera fracture, this eruption marked the collapse of the second caldera. The tuff exceeds 150 meters in thickness on Thermon Ridge. The Mesa Falls Tuff is a marker of the second volcanic cycle, which lasted roughly 750,000 years. Like the first, it followed a pattern: pre-collapse rhyolite, catastrophic eruption, caldera collapse, and post-collapse lava flows. But each cycle has unique features, reflecting changes in magma source and tectonic stress. The third volcanic cycle began after another long pause. The last supereruption, 640,000 years ago, produced the Lava Creek Tuff and formed the current Yellowstone Caldera. This event ejected about 1,000 cubic kilometers of material, creating the 60-kilometer-wide caldera that defines the park's central plateau. Post-caldera activity included rhyolitic domes and flows, such as those at Obsidian Cliff and the Pitchstone Plateau, as well as basaltic eruptions along the margins. The last magmatic eruption occurred about 70,000 years ago, marking the end of the third cycle. Hydrothermal explosions have also shaped the landscape in the Holocene. These are not magmatic, but caused by sudden steam bursts from superheated water. The Mary Bay explosion crater on Yellowstone Lake is one example, formed about 13,000 years ago. Over 3 cycles, Yellowstone emplaced 6,500 cubic kilometers of rhyolite and 250 cubic kilometers of basalt. Ash flow tuffs account for over half the total volume. Each cycle lasted about 750,000 years, with supereruptions separated by hundreds of thousands of years of smaller activity. The West Thumb Basin, formed by a third cycle explosive event, remains thermally active. It hosts hot springs, fumaroles, and underwater vents. This ongoing hydrothermal activity is a reminder that Yellowstone is not extinct. It is a living volcanic system, constantly monitored for change. The Yellowstone Volcano Observatory uses seismic networks, GPS, and satellite radar to track deformation, gas emissions, and earthquake swarms. No signs indicate an imminent eruption. The magma reservoir is mostly solid, with only 5 to 15% melt, far below the 30 to 50% needed for eruption. Public perception, fueled by films like Supervolcano, often exaggerates the threat. But scientists emphasize that Yellowstone is not overdue. Volcanic cycles are not periodic. They depend on magma accumulation, which varies. The next eruption could be small or large, but it is not predictable on human timescales.